So hello everyone. Today we have Dr. Nafiz Ishtiaque, and we are very happy to have him. He will give us three lectures in this school. So a bit about him: he did his PhD from Perimeter. He was a postdoc at Princeton, then IHES in Paris, and hopefully he'll join as a faculty in Shanghai soon. And about his research, he works on a lot of things actually. He he worked on integrability and some aspects of string theory, holography, topological field theories, and so on. So it goes on. So, and we are very lucky to have him here today. So hope everyone will enjoy his lectures. Thank you.
Uh, Thank you, Rakin, for the very kind and somewhat exaggerated introduction. Uh, okay, so today is going to be the second lecture of this GR course, following the lecture by Nabil, where he introduced manifolds, covariant transformations, tensors, and etc. So we are going to use some of the key results from that lecture today and going forward. The main topic that we want to discuss today is this introduction of covariant derivative, which is an important aspect of the mathematical framework behind GR. However, before we get into the technicalities, in the first one third or half, maybe even half of the lecture, I would like to discuss some basic motivations behind why we are going to introduce these technical tools to talk about GR. Because I assume that many of you are coming from courses such as classical mechanics or classical electrodynamics. And general relativity is also supposed to be a classical theory, so it falls under the area of classical mechanics. But if you just start talking about the mathematics of GR, like manifolds and covariant derivatives and curvature, etc., then it may seem a bit esoteric and it may not be obvious why this is related to classical mechanics. So let me start by trying to motivate what is the classical mechanical part of VR and then how that leads us to studying differential geometry. And then I'll start talking about covariant derivative and other things. So to begin with, the first part is going to be motivation. And as I said, I would like to connect this to classical mechanics. So the most familiar form of classical mechanics is, of course, say, Newtonian mechanics. So what do we study in Newtonian mechanics? We study the movement of point particles, right? So starting with Newton, so Newton has his famous equations of motion. F equals ma, or we can write something like this, right? And we're all familiar with equation of this type. So what do we study here? We assume that we have some particle that is situated at some location x at time t, and this particle moves with time along some trajectory, and that trajectory we find it by solving this differential equation, right? So what are the ingredients of an equation like this? One ingredient is the position of the particle, which tells us where the particle is. There's this parameter mass, and then there's some force that compels a particle to move. So here, there are actually two different kinds of information. One is the information about the state of the particle, where the particle is, and any other parameter such as mass. And the other kind of information is this force, which is responsible for the movement of the particle. Okay. So one type of information, which is kinematics, this is about states of your system. So this is about how to describe the state of a system. So what is the state of a particle? It's its position and its momentum. So in momentum, we are combining its velocity and its mass. So the position is, of course, obvious from here, but so where is the momentum coming from? So recall that if you want to solve a second-order differential equation like this, you have to provide some initial condition. So what are the initial conditions? The initial conditions are the position of the particle at time t equals to 0 and the velocity of the particle at time t equals to 0. So given this initial data, you can find a unique solution to this equation. So what we're saying is that if we describe the state of a particle by this data, then given any state or any starting condition of the particle, we can find a unique trajectory. So we can solve the problem of dynamics. Okay. And since the particle also has a mass, we combine that with the velocity to make it momentum. All right. So these two things together form what is called the phase space. All right. And then there's a part about dynamics. So what does dynamics do? So dynamics simply means that how the particle moves. So when we're trying to understand a physical system, it's not just enough that we are able to describe the different states of the system, but we would also like to be able to describe how the system evolves with time. And that's where dynamics comes in. So in this example of Newtonian mechanics, this dynamics is encoded in force. All right. So this is going to be the prototype of any classical mechanical system. So for example, by the way, I will from time to time take a look at the chat and see if there's any question. Okay. So what other examples of classical mechanical systems are we familiar with? Well, so after Newton, we can go up to Maxwell. And what I would like to highlight is that even though Maxwell's equations of motions are quite different, and a priori we are talking about different things, instead of point particles, now we're talking about electric and magnetic fields. The underlying structure is the same. The underlying structure is going to be that of a set of data describing the state of your system and something that governs the time evolution of that system. Okay, so in case of Maxwell's electrodynamics, what constitutes the states of the system? So how do we describe in which state we are? So that, again, you may already be familiar with. Let me remind you that the state of the systems, so the kinematics, are described by a vector potential and your electric. Okay. And just to clarify, so I am talking about the electromagnetic field, not a charged particle. Because there's a particle moving in uh, uh, deriving from the.
I don't know. I started recording again. Sorry.
Oh, sure, sure. Yeah, no problem. Um, yeah, I was simply mentioning that there's a completely equivalent formulation of Newtonian mechanics in terms of the Hamiltonian. Instead of writing it as a second order differential equation involving forces, you can also write it as follows. So you explicitly introduce the position and the momentum, and then you write down some equations of motion that look like um, yes. That look like this, where this Hamiltonian is a function that involves terms like momentum squared. There may be some numerical factors plus some potential, which may depend on everything you have, right? And the point is that you choose V in such a way that these equations become completely equivalent to this equation. So they're the same. There's nothing new. Sometimes we may favor this type of formulation because here we explicitly use the coordinates of your phase space, so these positions and momentum, as opposed to here we explicitly only see the position. Right? Okay. So in case of Maxwell, the analog is that the state of a system is described by a vector potential and an electric field. Um, and the role of the dynamics is played by some version of this Hamiltonian, which we can write down explicitly. And if you are not familiar with this expression, you don't have to worry too much about it. I'm just going to write it down for the record. It's the same expression. So here, the Hamiltonian is a function, of course, of the variables that you use to describe your system. So this A will be inside this B, and also you explicitly see the time component of A. And this rho and J, so these are some background currents and some background charges that can source electromagnetic fields. And if you write down the analog of these equations, starting from here, you will end up with the familiar Maxwell's equations. So the equations of motions. So again, I'm assuming that you have some familiarity with electrodynamics. If not, then you can kind of skip what I'm saying right now. But if you are familiar, then I would like to emphasize the idea that GR is just a natural evolution of this kind of formulation. So you follow this so there's a prescription for how to go from Hamiltonian and your state variables to your equations of motions. So you follow that in case of electrodynamics, and you end up with all right. So these equations, they are completely analogous to these equations or these equations, right? But one thing that is quite new in case of electrodynamics is that our variables that we use to describe the state of a system, they are now fields defined on the space-time, right? So these are functions of your position and time. So we see that in order to describe the state of an electrodynamic system, we have to specify some vectors at each point of your space at each time. So this simply means that you now have a lot of degrees of freedom. There are many different states that your system can be in, as opposed to a point particle moving in a space. The description of the state was very simple. You just had to specify a particular point in space where your particle was located, right, at a particular time. Now the states are a bit more complicated, but this is more of a technical difficulty than anything conceptually particularly new. So we're still just doing classical mechanics. And so here there are many more technical difficulties. For example, there are gauge symmetry. So this is not really the phase space. It gets reduced to some smaller space and so on and so forth. We are not going to delve deeper into these issues in this course. But just notice the similarity, right? So then the question is, what's different in GR, or is anything at all different in GR? And in principle, not really. So we can now jump back into GR. So here we were trying to describe the dynamics of a point particle. Here we were trying to describe the dynamics of electromagnetic field. And so electromagnetic field, so these are responsible for interaction between charged particles, right? And so now we are interested in describing the dynamics of gravity in some way. And we perceive gravity as a force between any two objects with mass, right? So the idea is that, so how do we describe that force? And let me see, were there any questions? So won't the Hamiltonian be better described with respect to the Faraday tensor and the four potential? Sure, yeah, you can do that. Which equation did you use for dynamics? What is it called? Which equation? Are you referring to these equations? So these are Maxwell's equations. I don't think people need to mention their name. Okay. Third equation should be called E is minus dB dt. This one here. Okay, yes. And should we be calling Maxwell's equation as equations of motion? Yes, they are equations of motion. All right. So now we are trying to do something similar for gravity, right? So historically, it seemed that gravity was just like any other force. So like the electromagnetic force. The electromagnetic force was responsible for the attraction or repulsion between charged objects, and gravity was responsible for the attraction between massive objects. So the first natural tendency when you're trying to find a theory of gravity would be to define a field or a bunch of fields on your spacetime, and then trying to find some kind of interaction between different objects, right? So basically, you try to find the analogs of these kind of fields for gravity, and then you try to find an analog of this kind of Hamiltonian for the fields that you introduce for gravity, right? So why aren't we doing that? Well, quite early on, people observed that there were some quite interesting features of gravity that were not present in any other theory that we studied before gravity. For example, from the time of Galileo, we know about a very interesting property of gravity, which is sometimes called the weak equivalence principle. Okay. So What is this? Notice a very curious feature. So from Newton's theory, we know that when we exert force on an object, it moves, but objects have inertia. So some objects that have a high inertia tend not to move very fast, and objects with lower inertia move faster, right? So basically, the equation is that F equals ma. And so here I'm going to put a subscript on m to remind you that m is a measure of inertia. So what this equation is telling us is that if we exert F amount of force on an object, then that object will accelerate, but the acceleration will depend on something called an inertia. If something has a very large inertia, then acceleration will be small for a given amount of force, right? So this is simply a measure of how resistant an object is to moving when there's force acting on it. All right. And then people studied, for example, electrodynamics, where the electromagnetic force on a charged object was proportional to the charge, right? I'm simply going to say that it's proportional to the charge itself. I'm setting all constants to 1. So let me just write that Q E. So what this equation is telling us is that if you put a charged object which has charge Q in an electric field E, it will experience a force which is simply given by the product. So it's proportional to the charge. Okay. Now, once it experiences a force, it will start to accelerate, and the rate of acceleration will be controlled by the inertia of that object. Okay, very nice. And you would not expect this Q to have any connection to this inertia, right? An object with very high inertia can have very low electric charge, no electric charge at all, or very high electric charge. They're completely independent. Fine. But what happens in gravity? So if you put a massive object in a gravitational field, so what is a gravitational field? I think maybe this was briefly mentioned in the last lecture. I don't quite remember that. So we can think of gravitational field as a scalar field. That generates a vector field by taking the gradient. And if you put a massive object in a gravitational field, so this is basically the acceleration, right? And if you put a massive object in a gravitational field, so this will have a gravitational charge, the analog of Q. I'm going to write this as m grav. And this will be the force experienced by that object. So it's a force, it's a gravitational force experienced by a massive object. All right. And again, once it experiences a force, it will start to accelerate according to this equation, and the acceleration will be controlled by its inertia. So in case of electrodynamics, this charge had nothing to do with its measure of inertia. So in case of gravity, again, you would not a priori expect its gravitational charge or its mass to have anything to do with its inertia. But of course, we know that that's not the case, right? This gravitational mass is exactly the same as the inertial mass. So people observed, it's an observation. It's quite a startling observation if you think about it, that the inertial mass is exactly the same as the gravitational mass, right? So how did people observe it? So you take this equation, right? So you put a massive object in a gravitational field, it experiences a force, the force causes an acceleration. So this equals this, and if m inertia is the same as m gravitational, then this acceleration is the same as this gravitational field. So what that means is that if you put some object in a gravitational field, then regardless of the mass of that object, it will accelerate at a fixed rate, right? So the acceleration of an object in a gravitational field does not depend on its mass. And that is a consequence of the fact that these two things are the same. Um, so um, and because of this, so the acceleration induced on an object by a gravitational field does not depend on the mass of that object. There is no mass in this equation. And this was supposedly the famous experience where Galileo dropped some objects from the Tower of Pisa. Um, anyway, so there's obviously something very special about the gravitational force. For any other force, well, at that time, the only other force that people were aware of, I think, is the electromagnetic force. But now we also know about the electroweak force, the strong force, etc. And in all of those cases, the charge has nothing to do with the inertia of that object. But only in case of gravity, the gravitational charge is exactly the same as the inertial charge, the inertial mass. Okay, so there is something special about gravity. And okay, so what is the consequence of the weak equivalence principle? Uh, mm, so what should be the statement? So basically everything falls with the same acceleration regardless of mass. So if you are falling with other objects, then you will see, relative to you, everything will seem to be floating, regardless of whether they're small or large, right? So basically, we can make a slogan that says that to a free falling observer, um, well, okay, let me just say things seem to flow. It's a silly way to say it, but anyway. Okay, so this is old news, right? We knew that a long time ago, long before Einstein. But Einstein at some point discovered special relativity. And after the discovery of special relativity, it kind of became apparent that mass wasn't really a charge like other charges. Rather, it was just a different expression of energy. So um, this statement that this inertial mass is the same as gravitational mass, it became slightly more plausible because there was something special about mass. It wasn't like any other charge. Like electric charge doesn't get mixed up with energy. Um, and eventually, Einstein proposed a somewhat stronger version of this equivalence principle, which we can call Einstein equivalence principle. And the slogan here is that what should I say? Okay. So before Einstein, we knew that when we are in free fall, things do not seem to be affected by gravity, right? Things seem to flow. So then Einstein strengthened this slogan by basically postulating that if we are in free fall with a bunch of other things, then it's not just that we should observe them to be floating, but it's that there is no experiment that we can perform while we are freely falling that would detect gravity, with some asterisk. The asterisk being that our experiment has to be confined to a small space, and we will get to that reason why later. For now, we can say it like this: that when we are freely falling, all of physical laws seem to be behaving in a way as if gravity did not exist. Okay, which again is quite startling if you think deeply about it, because in any other case, so for electrodynamics or any other forces that were discovered later on, regardless of your reference frame, you can always detect that something is going on. So if there is a charged particle emanating an electromagnetic field, then if you're accelerating with respect to the charged particle, or if you're accelerating along with the charged particle, the situation would be different, of course, but there would be an effect of electrodynamics, right? It's not that in one reference frame, there is no effect of electrodynamics. The charged particle has lost its charge and it doesn't interact with anything else. There will always be an effect. But in case of gravity, this principle tells you that it's possible to find a reference frame where there is no gravity, right? So it may seem a very trivial statement, but I want to emphasize the fact that it is, in fact, quite non-trivial. And it's basically this principle that lead us to study geometry when we want to study gravity. So why is that? Because the lesson that we learn from this principle is that gravity is not really a force, because a force is something that accelerates other object. Whereas, and a force is a physical thing, right? So what that means is that regardless of your reference frame, you may have different description of that physical thing, but you will have some description of the physical thing. But in case of gravity, depending on a reference frame, you may not notice it at all. So what we should say is that gravity does not necessarily act as a force, but what it does is that it gives you certain specific trajectories in space-time. And those are the trajectories where, if you're following the trajectory, you will be able to completely ignore the effect of gravity. So the point is, gravity draws certain special trajectories in space-time. Okay. So this is an important lesson. And so what are these special trajectories? So these are the paths you take when you are falling. Okay. So this is our first evidence that gravity has a very close connection with the geometry of our spacetime, right? Because it is kind of drawing certain special lines in our spacetimes. And later, when we have developed some tools, we will call this path geodesics. at this stage, we are not really going to worry about what the definition of these things are, right? So it's just that we have observed that gravity is different from the other forces, and there is some intrinsic way that it describes certain properties of the spacetime. So there are some distinguished lines in our spacetime, and if you follow those lines, then gravity completely vanishes. Okay. Um, and so even this doesn't tell you that you have to study differential geometry over spacetime, right? So it could be a lot of other things. That's why Einstein's theory was so ingenious that it found a very novel at the time way of describing gravity using differential geometry that actually works. So there is no proof that gravity has to be described in terms of differential geometry over spacetime. The only a posteriori proof, if you want to call it, is that it works. So we will define a bunch of geometric quantities, and then we will interpret those geometric quantities in terms of physical things, and that will lead us to some results of experiments that we can then verify. So I'm telling you simply to kind of motivate you to study differential geometry. Otherwise, you may ask, well, why do we study it at all? I mean, we are interested in gravity, which is a force between objects. So what does this have to do with covariant derivatives or curvature? Okay, so let's say that now you are motivated to study gravity as something geometric. How do you still fit that into this framework of classical mechanics where you have your phase spaces described by states and some equations governing dynamics, right? So what are your states in the theory of gravity and what is the dynamics? Well, so again, we do not have any a priori reason to be absolutely certain that this is going to be true, but what ends up being a sufficiently accurate description is that we can think of states as space. So let's say we are in four-dimensional spacetime, so our space is three-dimensional. So your state is going to be your three-dimensional space. Okay, it's hard to draw three-dimensional space and then drag it, so I'm going to draw a two-dimensional space. So something like a sheet of paper. And then as time evolves, the space can change because your state can change. And that evolution is going to be the dynamics in our theory. So at different times, so let's say this is at some time. And you have to take all of this with a grain of salt, right? Because to what extent you can define a meaningful time across the entirety of space is questionable. But okay, at least locally, this is what it's going to look like. So you draw your sheet at different times. And when you put all of this together, you get the structure of a spacetime, right? So now it's one higher dimensional object. So these are the same thing, basically. So if you kind of buy into this idea that our state should be described by space, then okay, so one question that you can ask, so what do we exactly mean by that? So previously, in the simplest case, when we said that our state is described by position and momentum, we had a very concrete description of that, right? So a position is a point inside the space. So it has, say, three coordinates, so three real numbers. Momentum is the same, three more real numbers. So we need six real numbers to describe the state of a particle. So in case of electrodynamics, it becomes a bit more complicated. But again, we have very concrete descriptions. At each point of space-time, we have 3 vectors here and 3 vectors here. So again, 3 real numbers here, 3 real numbers here. But now we have 6 of these numbers at each point of space-time. All right, that's fine. So what's going on here? How do we describe space? Well, that is going to be what we talk about today and in the upcoming lectures. But the idea is that we have to find some description of space. And obviously that is the realm of geometry. And not just of space, because if we look at the full evolution of space, it's a one higher dimensional space, the space-time now. And how things evolve is basically how this object looks like as you move in some direction, right? So basically now you can kind of convince yourself that you should study the geometry of 4-dimensional spacetime or 3 plus 1 dimensional spacetime, because that geometry is basically going to tell you what your degrees of freedom are, what these spatial slices look like, and what the evolution looks like, right? Okay, so what we learn from these kind of thought experiments and analogies is that we should study geometry of spacetime. All right, and that is going to be the more technical part of the lecture. Okay, so now before I move on to the technical part, let's see if there are any questions. Difference between M gravity and M inert. Right. Okay, so M inert is what comes out of Newton's principles, right? So Newton tells us that any stationary object remains stationary until there is some external force acting on it. And even when there is an external force acting on an object, it will try to resist motion. It will accelerate according to this equation, but the rate of acceleration will depend on something called an inertial mass. So some objects will have very large inertial mass for which, given a force, the acceleration will be small, and then some object will have a smaller inertial mass, which will accelerate faster, right? So that's where we get our idea of inertial mass from. It's an object's intrinsic resistance to motion. And gravitational mass is simply the analog of electric charge or any other charge you may be familiar with, which is that we know from experience that any 2 objects in the universe attract each other. So this is analogous to charged particles attracting or repelling each other. And the amount to which a charged object feels the presence of another charged object depends on something called the charge, right? So for example, in case of electrodynamics, if you put a charged object in an external electric field, the force it will experience will depend directly on its charge. This should be similar for gravity as well. If you put an object in a gravitational field, G, the gravitational force it experiences should be equivalent to its gravitational charge. And we call the gravitational charge the gravitational mass. It just happens to be the case that this gravitational mass is identical to the inertial mass. And there is no apparent reason why this should be true at all. This is a very surprising observation. But then, of course, now we know that the reason is that these 2 are, in fact, coming from the same space. I mean, coming from the same origin. Gravity is not, in fact, a mass, in fact, a force. Rather, it describes the geometry of your space-time. And when something moves in that space-time, of course, it detects where it's moving, right? So it picks up things from its surrounding. And that's why the same gravitational entity ends up in the inertia of an object. Okay, well, yeah, this was a bit hand-wavy, but I hope that answers the question. Of falling body experiments of falling bodies. I'm not sure what that means. The observation of freely falling bodies problem. I don't know the mass of the bodies. How does it imply the equality? The observation of freely falling bodies proves that the ratio of inertial and gravitational mass is independent of the masses of the bodies. Right. How does it prove the equality of the masses? Is that the question? So it proves equality because the gravitational field is fixed, right? And you place different objects in the same gravitational field, and you observe that they all have the same acceleration. So this is fixed, and this is an observation. You observe this by doing experiments. And for this to be true, given this equation, this inertial mass has to be the same as the gravitational mass. That's, well, again, it's not a proof, it's an observation, but yeah, that's where it comes from. When you say we should study geometry, you mean abstract geometry, right? Because we cannot really visualize. Yes, of course. Does GR account for the spacetime curvature caused by dark matter? Have there been any observations that detect spacetime curvature caused by matter other than the kind we are familiar with? Does GR account for the spacetime curvature caused by dark matter? I think so. So I'm really not an expert on this cosmological stuff, but yeah, basically, we observe expansion of the universe. Actually, well, that's dark energy. We observe movement of celestial objects in a way that is not explained by the observed mass. So the amount of curvature that should be present if the only mass in the universe was the things that we observed, then that wouldn't explain the movement of the thing. So there has to be something else causing the curvature, which are dark matter. Does each state corresponding to a point in time? If you are referring to state in gravity, then I'm assuming that's what you're referring to. Then no. So each state is not a particular point in space-time, but each state is one state is one whole space. So in order to describe the state, you need a lot of information. You need to describe what the space looks like at each point. And then, of course, you have a different state at each time. Newton to the proportionality constant in F equals Kma to V1. K equals 1. Okay. He did it so that M inert equals some gravitation. Sure. Yeah, you can say that there is some proportionality constant in Newton's equations, but okay, then you would have a constant hanging around. I mean, there are maybe other constants hanging around. I'm setting all the constants to 1. I mean, so what do you call an inertial mass depends somewhat on convention, right? I could call half of the inertial mass the inertial mass, but then the relation would be that the inertial mass is half of or twice the gravitational mass, so the surprising part is not that they're equal. The surprising part is that they are related by a simple equation. I think you meant to ask if each state corresponds to each instant in time. Yes. Each state corresponds to a particular instant in time. All right. I think that's all the questions. So now that we are kind of motivated to study the geometry of spacetime, let us now delve into covariant derivative. Okay, since this is a slight shift in topic, maybe we can take a 5 minutes break and reconvene at, let's say, 4. Okay, so it's a 3.5 minutes break. Okay, so we will be back at 4. 4 in Central European time. What is it? 8. Yes, at 8 p.m. Bangladesh time. And yeah, if you have any more questions, you can ask in chat, and I will try to answer. This question is covariant derivatives somehow related to tensor? Yes, they are. I'm going to start by talking about tensors and why partial derivatives fail in that regard. G and A are not equal but equivalent. Is that what you mean? Or you were talking about the mass, inertial, and gravitational? G and A are not equal but equivalent. Is that what you mean? Or you were talking about the mass, inertial, and gravitational? I'm not entirely sure what the question is there, but so and what I'm saying is that G and A do not have to be equal a priori, right? Um, but and so okay, so why do I say that? Because so G is some external gravitational field in which we put some objects, and depending on the masses of the objects, different objects could feel different amount of force, and then that different amount, and they do feel different amount of force, and depending on the amount of force, they would accelerate differently. That would be the naive guess. But by experiments, we observed that the accelerations of the objects were always equal to the gravitational field and had nothing to do with their masses. So what does it mean? That means that the gravitational force experienced by the objects, which was given by this formula, and the acceleration that we compute of an object that feels a force given by something like this is this. And we observe by experiment that A equals G, and that can only happen if the inertial mass and the gravitational mass are the same. So that was my point. So GR is a classical theory, as you mentioned at the beginning. What sort of problems arise when we try to make it a quantum mechanical theory, as there are quite a lot development QFT through QT? Yes, indeed. I mean, GR is a classical theory, and we have had great luck in trying to make quantum versions of classical theories. For example, electrodynamics or electroweak, but the electroweak didn't have a classical theory to begin with. But with electrodynamics, we have had very good luck, right? We have a very successful theory of quantum electrodynamics. But that has not really happened for gravity for various reasons. Of course, we are not going to talk about that in this course. We are only going to be talking about the classical aspects. But basically, we have not been able to find a quantum theory of gravity. I mean, at a zeroth level, when we try to do something analogous to what we did for electrodynamics, we really cannot compute Okay, so if you're familiar with quantum mechanics, in quantum mechanics, we compute probabilities of various kinds of interaction. Um, and when we try to do that for a naive quantum version of gravity, we don't get any finite answer. So certainly the theory that we have do not work. But it's a very complicated problem that doesn't have a solution so far. Could you say a bit about the Yod-Bus experiment regarding this inertial and gravitational mass? I do not know what that is. I'm guessing it's some experiment that tested the equality, but I'm not familiar with the experiment. It's difficult to think 3D space as state in time. Can explain it a bit further, like how can we visualize it? Yes. Okay. Um, so in case of a particles, how do you visualize the state of a particle? Um, Actually, so what do we mean by state? It's literally what it sounds like. You have to describe the system. That's it. So if the system is just a particle, then the description simply consists of telling your audience where the particle is and what its velocity is. That's it. Because at any given time, that's all you see. Uh, in case of electrodynamics, in order to describe the system, you have to explain that what your electric and magnetic fields are at each point of your space, right? So similarly, in case of gravity, so here again, so we are making a guess. We are guessing that this is the right thing to do, and our guess is that at each time we should describe what the geometry of the space is. And it's a very good question that how do we describe the geometry of a space? And okay, that's going to be the topic of this whole lecture series, basically. Um, so maybe it's better if I reserve that answer for the technical part. But yes, so it is a non-obvious question as to how to describe the geometry, but we will try to answer that. Hardy diagrams cannot be normalized. Yes, that's right. How did Einstein figure out that the differential geometry would be the perfect model? Were there any other notable attempts before? Why differential geometry from out of nowhere? Yeah, that is a very good question. Uh, how did Einstein figure out? I don't know. I don't know if anyone knows. Uh, yeah, it was a very clever move. Um, and also, we don't know if it is the perfect model. All we know is that it works for all of the observations that we have made so far. That does not mean that it's the perfect model. There can be better models because maybe we have not observed something yet for which gravity or GR will not be sufficient. Were there any other notable attempts before? That I don't know, but I think there was something about dimensional reduction from higher dimensional space-time. I don't know how successful that was. Obviously not very. Riemann invented differential geometry about 60 years before. Yes, of course. I mean, the differential geometry existed, I don't know if it was 60 years before, but geometry existed before Einstein. But no one thought about using that to describe gravity, right? Uh, there was no obvious reason why geometry should have anything to do with gravity. It was a brilliant idea. What is the best theory of gravity to understand inflation theory, which is responsible for formation of PBH, some kind of primordial black holes, I guess? Uh, I don't know. I am really not a cosmologist. What is it? Uh, but I think you guys are going to have some lectures on cosmology, so these things may be covered in those lectures. Okay. Uh, I think now we can move on to the covariant derivative part. Okay, so there was already a question as to how we should describe the geometry of space, right? And the answer is really not obvious, but we can try to, again, find some motivation in observation. For example, suppose space was just a 2D two-dimensional flat space. I'm going to talk a lot about 2D because it's easy to draw, but everything I say, you should imagine that there's some version of it in three-dimensional space and four-dimensional space-time. Okay, so if space was just a 2D sheet of paper, then if you took a vector and you parallelly transport that vector along some path, and then you parallel transport that vector along a different path, and then come back. So what happens? This vector gets transported, and then transported, and then transported back. So it comes back to itself, right? And while I'm saying this, I am relying a lot on our intuition about what it means for vectors to be parallel or parallelly transported. These things are less obvious than they sound, and we should really define them rigorously if we want to talk about them, but I am not going to do that because the intuition is really the most important thing here. I will define some parts of it. So on a flat space, if you parallel transport a vector along a closed path, it comes back to itself. Nothing has changed. But if space were, say, a two-dimensional sphere, what would happen then? So let's take a 2D sphere, which has a pole, which has another pole somewhere else. And you can connect two poles by some path. And you can draw an equator. And there are going to be other paths connecting things. Okay. Let's say that this angle is 90 degrees, 90 degrees, 90 degrees, 90 degrees. So what happens if you try to parallel transport a vector along this closed path? Okay. So here we had a path, a triangle. Here we have a path, which is kind of a triangle. Now let's take a vector like this. So if you parallel transport this vector, so at this point, it will look like this. Then it will look like this as you come down here. And then as you return to your original point, it is now totally different. You started from something like this, and after a parallel transport, you ended up with something like this. So even if you did not know that you were on a sphere, and you only had access to part of it, which locally looks like flat, right? That's why we have flat earther people. You could still tell by doing this experiment that you are not really on flat space. Because if you were on flat space, then you would expect your vector to come back to itself, which does not happen here, right? So there is some geometric information encoded in the local picture, right? So locally, we should be able to define something that will tell us when our space is not flat, when it has some kind of curvature. In this particular example, what is the thing that we used to distinguish this space from flat space? The thing that we used was this idea of parallel transport. So this is kind of our first hint that being able to parallel transport vectors from one point to another point over spacetime is an important geometric construction that has a lot of information about the curvature of your spacetime. Okay, so we really need to be able to define parallel transport, and so I don't know to what extent you are familiar with parallel transport. So let me say something very basic. If it's too easy, I think that's fine. So for this experiment, we really need to be able to parallel transport vectors, right? But much easier than parallel transporting vectors is parallel transporting scalar. So basically, so what do we mean by parallel transporting scalar? So suppose um, you have some space-time, and you have a scalar at some point, which just means that you have a number at a point. So what does it mean to parallel transport that number to a different point? Or rather, what we really want to do is that if you have a number at every point of your spacetime, which is another way of saying that you have a scalar field, then you may want to ask whether those values of your field at different points are parallelly transported. So you want to compare the two different values of your function or your scalar field at two different points. So let's say that your field is phi, and the 2 points that where you want to compare the values of this phi is x1 and x2. So you want to compare phi x1 with phi x2, right? And let's say that x2 is x1. So let's say this is x1 and this is x2, and this distance is delta x. Again, I'm being very hand-wavy about what I mean by distance and straight lines and so on. But again, rely on your interest on flat space. So suppose x2 is x1 plus delta x. This figuration doesn't really make any sense on curved spacetime, right? If you think carefully, but let's say that we're on flat space. So how do we compare x2 with x1? So phi x2 is phi x1 plus delta x. Now we can use Taylor expansion, right? So it's phi x1 plus delta x times del phi del x plus higher derivative terms, delta x squared by 2 factorial, and so on and so forth. Once you can take one derivative, you can take multiple derivatives. That's not a problem. But really, so the idea is that in order to be able to find the value of your function at a point x2, when you only know the value of the function at x1, you need to be able to differentiate that function, right? So knowing the derivatives of a function at a point allows you to extrapolate that function from that point to a distant point. This is kind of the idea of parallel transport, that we want to be able to tell what some field looks like at a point that's far away from where we are. And in order to be able to do that, we need to be able to differentiate that thing, right? So when I say that we need to be able to do parallel transport, what that really means is that we need to be able to take derivatives of things. Taking derivatives of functions is very easy. And again, I'm going to assume that you guys are at least somewhat familiar with multivariable calculus. So then you would say that, okay, so taking derivatives of vectors or tensors is also easy. Just take partial derivatives. And that's a perfectly fine answer. That is a derivative. But as we saw in the last lecture, that when we talk about manifolds, it is very important that the quantities that we use to describe things, that they be tensors, meaning that they should transform in a very particular way when we change the coordinates. Now, let's quickly recall why that was the case. It was the case because in case of a flat space, we can just put some coordinates that look like R2, right? So we can say that this is my x-axis, this is my y-axis, and there is some grid, and we call these 1, 2, 3, 1, 2, 3. And using this grid, we can identify any point in that space, anywhere, regardless of how far that is, right? We don't ever have to change coordinates. This is perfectly fine to describe flat space with a single coordinate system. But we don't know if our spacetime really is just flat space. I mean, okay, there are matters, so because of matter, there are local curvatures, so it's not flat in that sense. But let's forget about matter. Even in the absence of matter, we do not know if our spacetime is really flat. And if we are on a manifold, even something as simple as S2, there is no way that we can put a grid that covers the entire space unambiguously and makes it look like R2, right? Because it's compact. R2 is not compact. I mean, if I keep going this way forever, and if I keep going this way forever, we are not going to end up in the same place on R2. On S2, that is going to be the case. If you keep going in this direction, you will eventually end up here. If you keep going in this direction, you will eventually end up at the same place. So we cannot say that they are both the infinity in this x direction and infinity in the y direction. That's definitely not true. So if we want to put grids on S2, we have to use at least two different grids. So one that kind of covers the upper half, and another one that kind of covers the lower half. This is a horrible picture, but the idea is that in order to describe S2, we need at least two different coordinate patches. Okay, so talking about general manifolds forces us to study things that transform nicely when we change coordinate systems. And that is where we encounter our first problem with partial derivatives. So let me give you an example of where things go wrong if we just study partial derivatives. So suppose, so what is the issue here? So one can ask, why covariant derivative? Which is another way of asking what's wrong with partial derivative. Well, the answer to that question is that partial derivatives are not tensors. And we are going to see why. Now, okay, so suppose we have some vector field V, which has some index nu prime in some coordinate system. So I'm imagining that I have two coordinate systems. One is going to be x mu, and the other is going to be x mu prime. Okay, and I have some vector field V mu prime here, and some vector field V mu. I mean, the same vector field, but written in a different coordinate system. And we know how to relate these components, right? Using the transformation rule for vectors. Okay. Now, what if we had a derivative acting on a partial derivative acting on this vector field, right? So let's say that we have something like this: del mu prime, v mu prime, and we want to. So this is some quantity. Okay, they don't have to be the same. This is some quantity written in some coordinate system, and we want to write the same quantity in this coordinate system and see how they are related to each other, right? So the things that we're going to use is the transformation rule for tensor and the chain rule for partial derivatives for the partial derivative. So what is this? Okay, so this notation, it simply means x mu prime. Okay. Actually, yeah, let's stick to the bigger notation. This is just the chain rule on partial derivatives. And Then we have to apply the transformation rule for vector. Hopefully you guys remember what it looks like. Um, okay, so let's break it down. So act with the partial derivative on this and on this. So use the Leibniz rule for derivatives. So from the Leibniz rule, we get two terms, right? So one term is where this is acting on the vector itself. So let's write the term first. And then we have another term where this derivative acts on this derivative. All right, a simple computation. But now notice that this term looks exactly like how a 1, 1 tensor should transform, right? So imagine a situation where we don't have this term. If it were 0, then we could say that this quantity, which has an upper index and a lower index, is really a 1, 1 tensor. Because this is how a 1, 1 tensor should, a 1, 1 tensor written into different coordinate systems should be related to each other, right? So on one hand, we have the partial derivative of my vector components in one coordinate. And on the other hand, we have the same vector, right? The same vector written as a partial derivative of the vector in a different coordinates. And then we have these two Jacobian factors, as there should be in a 1, 1 tensorial transformation. However, this is not in general 0, right? Because nothing tells us that these coordinate transformations should be linear. And if the coordinate transformations are not linear, meaning that if these x mu primes are not a linear function of this x mu, then the second derivative is not going to vanish. Okay, so this is not 0 in general. And then this object does not transform like a tensor, right? So this is where we kind of run into a problem with partial derivatives, because we only want to use quantities that transform nicely when we go from one coordinate to another coordinate. And partial derivative does not produce quantities that transform nicely, okay? So this is the reason why partial derivatives are not tensors. All right. We have to remedy this, right? Because if we cannot define derivatives of things, then we cannot define parallel transport of things. And if we cannot define parallel transport of things, then how do we detect curvature of your spacetime in this way? Well, maybe you can say that maybe there are some other ways of detecting the curvature. And maybe that's true. But you must agree that being able to take derivatives is kind of a very basic operation that if we cannot do that, it's hard to imagine how we're going to compute anything. So let's better try to find a good definition of a derivative that behaves nicely. Now it kind of becomes somewhat non-canonical in the sense that you can ask, how should we define a derivative? I mean, in case of the partial derivative, there was a very natural definition in terms of limit, right? So you have some quantity, you compare them in neighboring spaces, you divide them by the small distance, if there's some limit, okay. There's some definition coming from real analysis. If we are going to forget about that and we are going to define a new derivative for ourselves, what should be our starting point? What properties should this derivative have? And so here we are going to mimic the partial derivative as much as possible. Okay? And in fact, when our spacetime is flat, our derivative should be the partial derivative. Okay. So let's first introduce a notation for our covariant derivative, which we are going to call this nabla. So in case of partial derivatives, we were writing this as del mu prime, right? And so we're kind of modifying this notation, and we're going to write this as this del mu prime. All right. And on flat space, this is a 1,1 tensor. If you're on flat space and you only do linear transformations, then this will transform like a tensor, right? Because this will vanish because your transformations are linear. So linear transformation means that you only have rotation and translation. So you have your Cartesian frame. You can rotate it, and you can move it around, but still it remains Cartesian. So when we're only talking about these kind of coordinate systems, our derivative should reduce to the partial derivative. So that is going to be one criterion. And what are some other nice criteria of derivatives that we know of? So the derivatives are linear, right? Properties of covariant derivatives. That we want. Again, this part is important, right? Nothing is forcing us to choose these properties. It's simply that these seem like nice properties, and they are as close to the partial derivative as we possibly can be, which is a reasonable idea. So first, let's number them. First, we want them to be linear. So what do we mean by that? If we take derivative of the sum of two things, where these things are constants, alpha, beta, then this should be this. Okay. I think you will all agree that this is very reasonable. Another extremely important property of derivative is that derivatives follow Leibniz rule. So it can be distributed over products. And again, we want that property to hold. So what does this mean? Okay. And I'm writing these properties for the simple case where these are just vectors. But of course, these equations we want them to be true when they're arbitrary tensors, right? So when we have more indices here and more indices here, and similarly. We just put the indices in the right places. Okay. So these are the two properties that we can start with. Right. So let me see if there are any questions in chat. Gross one. Okay. You were talking about parallel transport and then talked about differentiability. Can you clear the transition? I think a field is differentiable even on sphere where parallel transport changes the vector orientation, isn't it? Yes, absolutely. So I'm not exactly talking about differentiability, but even before that, I mean, even in order to be able to talk about whether things are differentiable or not, we need a derivative. So what I was saying is that in order to be able to transport things at a distance, we first need to be able to transport things infinitesimally. And being able to transport things infinitesimally means being able to compute its derivative. So we need some notion of derivative. And of course, we already have a notion of derivative called the ordinary partial derivative. But then we checked that it does not transform covariantly like a tensor. So we need a different notion of derivative that we can use to transport things first infinitesimally and then at a finite distance. And furthermore, that also transforms like a vector. That's where I'm coming from. So I want to be able to differentiate things, and I want derivatives of things to behave as tensors. I mean, derivatives of tensor to behave as tensors. Mm. Partial derivatives depend on distance as well. Partial derivatives depend on metric as well. Why is that? I think you can talk about partial derivative without ever referring to a metric. For example, in multivariate calculus, when you talk about derivatives and integrations, I mean, there is no metric to speak of, right? Well, in case of integration, there is some idea of a metric. But when you're just talking about differential calculus, you don't ever have to introduce a geometry. It's just limits of things. I mean, it happens to be the case that that derivative behaves well with a particular metric, the particular metric being the flat metric. But you don't need the metric to be able to define the derivative. And in fact, you actually don't even need a metric to define a covariant derivative, as we will discuss. The covariant does not have any limit-taking definition like the partial derivative. That's a good question. Does have a definition like a limit? Um, Not entirely, meaning that you cannot just define the covariant derivative using only limit. As we will see that the covariant derivatives are going to have some relation to partial derivatives, but it will have also some extra information that is not inside the partial derivative. So the part that corresponds to the partial derivative, again, you can define it using limit, but the part that is independent of the partial derivative cannot be defined using a limit. But to define the limit, don't we use the notion of metric? Okay. So, yes, you're right. So to define the limit, you need a notion of big and small. Yes, that is correct. That is correct. What I mean to say is that mm, so that notion of metric that is used to define the limit where something goes to zero. So recall that where that something that small comes from. It comes from really the real number, right? So it's a property embedded inside the real numbers. So inside in real numbers, we have a notion of when one real number is bigger or smaller than the other, and there's something called a zero real number, and then you can take a limit. So you're right that there is a notion of a metric, but this notion of metric is intrinsic to the number field that you're using. It is not a property of the space on which you're kind of doing this calculus. Now, you can translate that property of real numbers to the property of space-time. And that is what will define the flat Euclidean metric or flat Minkowski metric on your space-time. But you don't have to go there. You can just stay in the realm of real analysis. That's what I meant. But you're right. There is a notion of metric in real numbers, and that notion can be translated to a metric on space. But it's one extra step that you have to do to define the metric on space. Okay, very good question. All right, so now let me move on and see what are the consequences of these two rules. So one consequence which, let me see. I think I will relegate some computation to maybe exercises, but yeah, let's try to motivate things first. So first question is, if so we have found two properties that we like. Now, can we actually find an operator like this? Uh, okay, I forgot to mention a very important part of this definition. What do we even mean by a covariant derivative? So the idea should be that this is an operator that takes a PQ tensor and produces a PQ plus one tensor. And this is implicit in our notation. So suppose you have a PQ tensor, which means that you have mu1 dot 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 mu p, and then mu1 dot mu q. And if you take a derivative of this thing, you add another covariant tensor, right? So you go from a PQ tensor to a PQ plus one tensor. All right. Okay. So we are looking for some kind of operation like this that has these properties. So the first question that we must ask is, does an operator with these properties even exist? Well, we almost had one with the partial derivative, right? Because notice that the partial derivative will satisfy both of these properties. Of course, it doesn't satisfy these properties, right? It does. If you give it a PQ tensor, it doesn't really produce another tensor because of this failure to transform like a tensor. But it does satisfy these properties. So it doesn't really answer our question whether a tensorial operation satisfying these properties exist. Now, the actual answer is that, so the answer may not be obvious at first, but what turns out to be the answer is that yes, there are, and in fact, there are a lot of these kind of operations that satisfy these two properties. Infinitely many, in fact. So suppose we somehow manage to find two such operations, okay? So let's call one of them del and the other one del tilde. Okay. Suppose we have two of these operations that both map tensors to tensors and are linear and follow the Leibniz rule. Then how do we expect them to be related, or how different can they possibly be? So here I am going to state a result that I may not have time to prove now. If not, okay, if I have time at the end of the lecture, I'll prove it. If not, this will be an exercise. Let's see. So let me first state the result. And it may not be clear what I mean by this, so let me write down the equation. Suppose you take the derivative of a vector. suppose you compute this, and you compute the derivative of the same vector with respect to the other derivative. And what we want to know is how different can these two things be? So what this statement is really about is that it tells you that if you subtract these two things, then the difference must be given by a particular kind of transformation of this vector. Let's say something like this, where this is a tensor. Okay. So this is an important result. Let's see, are there any questions about this? So let's think a bit about what this really means. Because, so you can say that, well, by definition, this has to transform like a tensor, this has to transform like a tensor, so their difference must transform like a tensor. And these expressions obviously depend on V, both of them. So whatever tensor this is, it should depend on V. So there should be a V, and then it should be a tensor, so you kind of find a way to put a bunch of indices so that you have the same kind of indices on the left-hand side and on the right-hand side, right? Fair enough. But nothing tells you that there cannot be other derivatives of this vector here, right? So you could easily imagine that there may be situations where you have things like this, and then you have even more complicated tensors contracting everything and then putting in the right tensors, right? And again, derivatives with respect to the other derivative, and et cetera, et cetera. You could have higher derivatives, right? So the point is that this is obviously a tensor which has two indices. So what's going to be on the right-hand side is obviously a tensor that depends on V with two free indices. But in general, there is nothing stopping you from having terms that involve higher derivatives and higher derivatives of this vector, right? But this result tells you that all of these things vanish. There is nothing else but the first term, where you just have the tensor of the vector that you were differentiating to begin with, and a simple linear transformation of that vector. Okay, so that's where the power of this statement is, which is that given any two derivatives satisfying these properties, actually, this is a property of the derivative itself, not necessarily of covariant derivatives. So let me point out that these two properties define a derivative. And this property makes it covariant, that you map tensor to tensor. And this thing that I'm mentioning, this applies to derivatives, not, they don't even have to be covariant. So let me write two derivatives. Okay. So the proof of this, probably I will not have time to show you. So you can find it in World. Where in World? World section 3.1. Okay. All right. So this is obviously a powerful statement. It tells you that there are infinitely many terms that could be here, but none of them are here because they all vanish. How can we use this for our benefit? Well, observe that this holds for any two derivatives. They don't have to be covariant. And our partial derivative is a derivative, It's not covariant, but it satisfies both of these properties. So what that means is that you can always take a covariant derivative and compare it with a partial derivative. Actually, wait a moment. Let me correct it. It's not really tensor, it's just linear. Okay, so what is the difference? So tensor is something that has to transform in a very nice way, right? That has to transform like this. But a linear means that it doesn't involve derivatives of v, right? There are no derivatives here. It's just a linear transformation of a vector without any derivative, but it may not transform very nicely. It will be a tensor if both of these are covariant, but if I replace the covariant part with just two derivatives, it will still be linear, but it may not be a tensor. Okay, and this is the version of this statement that we are going to use because as our delta tilde, we can simply take a partial derivative. And then what it tells you is that any covariant derivative can be written as a partial derivative plus a term that is linear. Okay. So this implies for any covariant derivative, we have a formula like this. Okay. And this really is powerful because it may have happened that if you break down a covariant derivative, writing down first a partial derivative, then you have to add infinitely many terms involving higher order derivatives and higher order derivatives of your field, right? That could have easily happened. But this property tells you that, no, you don't have to worry about that. The difference between any two derivatives is always going to be a linear transformation of your tensor or vector. Now, this will not be a tensor if both of them are not tensors. So in particular, if you write partial derivative, which is not a tensor, this will not be a tensor. That's fine. So now the question is, we know that this is not a tensor. So, but we want this to be a tensor, right? Now we want to impose this covariance constraint on this. So the question is, how does this, what properties should this linear transformation have so that this is a tensor? Okay. And again, this we can easily figure out. So what is going on is that, let's again reserve two different coordinate systems, x mu prime. And in these two coordinate systems, we have these quantities, v nu prime. So, and we want to impose the constraint that this and this are related by a simple tensorial transformation. Someone asked for a proof of that property in Slack. It's in a book. I can send the link to the book, I think. Yeah. I think that would not be illegal, right? Well, okay. I can tell you how to find that book. Actually, it may even be on Wikipedia. Anyway, I'll send you the link. Yeah, sure. All right, so let's compare these two quantities, and we will impose tensorial transformation for these two quantities. We already know how this transforms. Not like a tensor, it has some extra terms. And then we will define a transformation for this quantity such that it exactly cancels that extra term coming from here, right? And that will tell us how this should transform. So let's start the exercise, and then you can finish it later. Again, let's use our chain rule and so on. So we have already said that we can write this derivative as partial derivative plus something. Actually, so I was using this symbol C to refer to the difference between any two derivatives, but when one of these derivatives is the partial derivative, this symbol is usually written with gamma. And in that case, this is also referred to as a Christoffel symbol. So we can transform this using this. I mean, you have to substitute this, right? Okay, it's a substitution, so I don't have to write it again. And here we have this additional term, and we know how vector transforms. So let's substitute that. And just to be clear, this is identical to this. Okay. Now we impose. So this means that this equality does not follow from here, but rather we want it to be equal to this expression, because this is how a tensor should transform, right? And we have an explicit formula for this, and we have an explicit formula for this. Once you compare the two expressions, you will find I mean, so recall that in here you also have this is this. So once you compare the expression coming from here with the expression coming from here, you will be able to find a relation between this gamma with unprimed indices and gamma with primed indices. Because this equation must hold for any v. So you collect the coefficients of v, you set them to be equal, and you find a relation for these Christoffel symbols. And the relation that you find is going to be It looks like a bit of a messy equation, but nonetheless an important one. So it shows you that these Christoffel symbols, they do not really transform like a tensor. This first part is a tensorial transformation, but then you have some part which is really a consequence of having to cancel this additional part coming from the partial derivative, which is why you have this second derivative hanging around. Right? This is the term that makes it not a tensor, but that's fine. Now, what we have is an expression of any covariant derivative written in terms of some quantities that we don't really know what they are. In fact, they can be anything as long as in different coordinates we relate them in this way. So the idea is that you start in a particular coordinate patch. You take an arbitrary object that has three indices. You call it your Christoffel symbol. And you define a derivative by adding this symbol to your partial derivative. And then when you go from one coordinate patch to another coordinate patch, you extend these Christoffel symbols by transforming them using this equation. And this defines a covariant derivative for you on all coordinate patches of your manifold. And in this way, you end up with a covariant derivative everywhere on your manifold, right? So this is a proof of existence by construction. We have explicitly constructed a covariant derivative on any given manifold. And in fact, we have constructed infinitely many of them because in the coordinate path where you're starting, there is no constraint on what these things can be. They are completely arbitrary. You can choose whatever numbers you want for each choice of indices, right? So there are many, many, many covariant derivatives. Okay. Now, since today I'm kind of running out of time, I think I was going too slowly. I will mention a few more important constructions, and in the next lecture, when we discuss geodesics, we will again have to say some things about parallel transport because it's integral to the construction of geodesics, and then we'll flesh out these things later. So notice that so far, we have not mentioned the metric at all. So far, no metric. Okay, so you guys are already familiar with the metric, and maybe you have come to think of metric as an integral part of a manifold, which is definitely true. But I would like to point out the fact that in order to be able to define a covariant derivative, you do not need a metric. Without a metric, you can define the notion of a covariant derivative. In particular, you can define the notion of parallel transport. And as we saw in this kind of toy example, once you have parallel transport, you can kind of detect whether your spacetime is curved or not. So this tells me that even in order to be able to detect some kind of curvature, or in order to be able to define the notion of curvature, you do not necessarily need a metric, but you need a connection. Sorry, you need a covariant derivative. Okay. And people will also refer to it as a connection. And these terminologies are almost interchangeable. So a connection sometimes refers to a covariant derivative itself, but it can also refer to just the Christoffel symbol. Okay. Actually, yeah, I'm not 100% sure whether connection refers to the full covariant derivative or the Christoffel symbol. I think people use it as both. Okay, but the point that I'm trying to make is that you can define curvature without a metric using only the idea of a connection. This is useful when you are talking about somewhat more abstract things, not just tensors, like spinors and so on. But for our purposes, we really want a metric. And as we were saying, that there are infinitely many, many Christoffel symbols that we can choose. So the conditions that we put on our derivatives were not particularly constraining. We still have infinitely many. So we are free to choose some more constraints. So the idea is that put more constraints on derivatives. Okay. So when we have a metric on our spacetime, we will put two more constraints in addition to the two that we already have. We are going to assume Actually, even before that, we are going to put some constraints. So I'm going to write down the constraints now, and I'm going to talk about their significance during the next lecture, which is that we want the operation of taking derivative to commute with the operation of contracting indices. And we want the covariant derivative acting on a scalar to just be the partial derivative. Okay. These are somewhat milder conditions. And furthermore, once we have a metric we will put even more constraints. We will want the metric to be covariantly constant, and we will want our Christoffel symbol to be symmetric under these two indices. Okay. I am mentioning this really at the end of the lecture because, as I was highlighting, that in order to be able to define a derivative, you do not necessarily need these constraints. A derivative is something that is linear and satisfies Leibniz condition. And it is covariant if it transforms tensors to tensors. That's it. That's a covariant derivative. But in practice, we want some covariant derivatives with some specially nice properties. And in order to identify those especially nice covariant derivatives, we put more constraints. So in the next lecture, I will show that once these constraints are put on your covariant derivative, you would really only have one covariant derivative left. So out of the infinitely many that you could choose by choosing arbitrary values of these Christoffel symbols, you will have one left. And that will be called the Levi-Civita connection. And that will have some very nice properties, which we will discuss more in the next lecture. All right, so let me stop now and see if I can answer a few questions before I end today's lecture. Can we have lecture notes for today's sessions? So I will, I think Nabil will send the PDF of his lecture to you guys, or either in email or in Slack. So I will do the same. It would be very helpful if you upload the lecture. Yes, I will. Can you share written slides? Yes. If we define a covariant derivative, do we have a notion of a reverse map then? As in, like, okay, that's a very good question. The answer is no, we do not. And what? Oh, sorry. The reason that so notice that different things can have the same derivative, even in case of functions, right? So two functions can differ by a constant and still have the same first derivative. Which means that if you only know the derivative of something, you do not necessarily know uniquely what that thing was, which is why a derivative operator is not invertible. Can you briefly talk about condition 3? Actually, so I will talk not just briefly, but at length about all of these conditions in the next lecture. So maybe it's better to do that rather than saying something incomplete now. Okay, so then I think that is the end of this lecture. You can maybe